Starting question 1, 2023 test 3. What would be the effect of intravenous administration of normal saline on urine output if fluid loss is the cause? Now we know normal saline is 0.9% sodium chloride, and this is intravenous administration. You're administering this 0.9 sodium chloride into blood, direct into blood. So imagine someone lost fluid and then you administer normal saline. You want to find out what will be the effect after you administer normal saline. Is it going to increase urine output, normalize urine output, decrease urine output, or none of these? So for normal saline, if lost fluid someone lost fluid and then you administer normal saline, is going to increase urine output. It's going to increase urine output after someone lost fluid and then you administered normal saline. Okay, try to think a bit of it. If someone loses fluid, the fluid that they've lost, more we are thinking about that fluid being extracellular fluid, ECF, because you don't usually lose fluid in the cells. So for example, maybe someone lost blood or something like that. So that means that because they've lost that fluid, the volume outside the cell has decreased. If you administer normal saline, of course normal saline has got almost the same concentration as the concentration inside the cell. But when someone loses fluid, mostly what they are losing is water. If you add normal saline plus that, meaning that because they've lost water, if you lose more water, what are you remaining with? You are remaining with a solution that is a bit more concentrated, right? And because of that, and then you administer also normal saline, you are adding more of the fluid. So meaning you are topping up more fluid to that solution that had which was more concentrated. Hope this is making sense. To a solution which is more concentrated, which remained, you are topping up more fluid. So what happens is that as the fluid gets to flow to the kidney, now you have added remember, you are adding this fluid in blood. So by the time you reach to the kidney, and we know that on the kidney there's going to be exchange of fluids move out of blood, they are going to go into the Bowman's capsule, others will be going into the proximal convoluted tubule. Now because you added normal saline which has got a concentration that is more as that of the cell, meaning that now you have diluted, it's more like you have added more water to the blood by the normal saline. So that volume is going to be dropping. How? By you removing some of that fluid from the blood into the renal corpuscle, into the collecting tubules. So fluid is moving out of the blood, it is going into the collecting tubules. So there's an increase in urine output. What would be the effect of intravenous administration of normal saline on serum creatine if fluid loss is the cause? Now, if you want to find out here we're not talking about the effect of normal saline on urine, but on serum creatine. Creatine is a product that comes out of muscles in the when you're exercising. So what happens that on serum creatine, when you administer normal saline, you are going to normalize serum creatine if you had lost fluid. So you had lost fluid and then you are administering normal saline. You want to see the effect of on serum creatine. It's going to normalize it. Doesn't increase it, doesn't reduce it, just normalizes it. Question 3. What would be the effect of intravenous administration of normal saline on urine output if acute tubular necrosis is the cause? Now, acute tubular necrosis, there is a problem with the tubules in the kidney. So here what happens that there is a problem with the tubules, meaning that there is a problem with the way the kidney is going to be able to function. So if you want to see the effect of you administering normal saline on urine output. Now, if you administer normal saline and then you want to see how it to affect normal output, the problem is not on real on more the fluid. The problem is with the kidney itself because of the acute tubular necrosis. So even if you administer normal saline, there is not going to be any increase in our urine output. So the best answer here would be B, because there is no increase in urine output. And then question 4, what would be the effect of intravenous administration of normal saline on serum creatine if acute tubular necrosis is the cause? Now here we're not talking about the effect on urine output. We are talking about the effect of on serum creatine. The effect of on serum creatine if you administer in normal saline and then there is a problem with the tubules. Here there is not going to be any rapid change in serum creatine. Of course, there's going to be a bit of change in serum creatine, the creatine that is in the blood, but the change is not going to be that high. So there's not going to be any rapid change in serum creatine. Number 5, does normal saline stimulate diuresis and does it cause natriuretic? Diuresis is the movement of water. Natriuretic is the movement of sodium. So normally, normal saline does not affect the movement of water. It does not also affect the movement of salt because normal saline has got the same concentration as the concentration inside the cell. So if you inject it, if you let's say you add normal saline, normally it's not supposed to affect the movement of water nor the movement of salt. So we can say normal saline is a weak stimulus of diuresis, and then B saying normal saline is a strong stimulus. It's not a strong stimulus really. And then for C, normal saline is both a weak and strong stimulus of diuresis. So that is just speaking against the statement. At the same time, you can be both a weak and a strong. So the best we can choose here is option A. Does not, it's a weak stimulus. What is the maximum bladder capacity of the average adult? Now when it comes to the bladder, when the bladder fills to up to somewhere between 120 and 320 mils, that is the mean that it can fill, that's the average. So between 120 and 320, and you can take the middle which is like 220 mils. That's a mean that a bladder can have, mean amount of urine. If it fills beyond 220 mils, someone will feel like urinating. And then the bladder can fill all the way up to 500 mils. But beyond that, it will start paining. So meaning that the maximum the bladder can fill is 480, which is like the 500 I've talked about. In an adult at rest, what percentage of the body's blood flow do the kidneys receive? So we talked about this, remember, in the class that we had. So the kidney, just like also the muscles, receive 25% of the total amount of blood that goes out of the heart. Approximately how many nephrons does the human kidney contain? The human contains 1 million kidneys, I mean nephrons in each kidney. So that is going to be 1 million. Which one is 1 million here? Okay, the option for 1 million, I didn't even include it. So that was option C. 1 with 6 zeros. Number 9. Which statement regarding a human kidney is true? Okay, this one. Which one can you pick? You are comparing the cortical nephrons and the juxtaglomerular nephrons. Which ones are abundant? Yeah, the cortical ones are more abundant than the juxtaglomerular. So that's 80% to 20%, option C. Which statement regarding the afferent arteriole is the in the renal glomerulus is true? We know afferent. We have got a blood vessel that is taking blood. Here is the Bowman's capsule. So this is the afferent where blood is coming from in that direction. Then when it's coming out of, that's the efferent. So which statement about the afferent is true? Mean blood volume changes in the circulation are not experienced in the afferent arteriole. Remember, we want what is it? True. Okay. Now, mean blood pressure changes are going to be experienced. This one is saying are not. Okay, mean blood pressure changes are going to be experienced. If there is a change in blood pressure, it will also be experienced in the efferent arteriole. Mean blood pressure is greater than is found in the arterioles elsewhere in the body. Now, this statement is necessarily not true because the mean blood pressure is supposed to be the same in all the blood vessels. This is, remember, the mean supposed to be the same. Mean blood pressure is less than is found in the arterioles elsewhere in the body. That is also not true. Mean blood pressure is much the same as found in the arterioles elsewhere. So this is the correct statement. Blood passes from the capsular space through. Okay, this is the one we are talking about here. So if fluid is supposed to move out of this region to come here, what structures is it supposed to pass through? The capillary endothelium and basement membrane, capillary endothelium, the basement membrane, and the podocytes, capillary endothelium, the basement membrane, and between the food processes of the podocytes. Which one can you pick? Okay, so when you are coming from the capillary to go into the Bowman's, into the this region, which is the collecting tubules there, or the renal tubules. The first thing you have to pass is the blood vessel. Now the blood vessel has got the epithelial cells, which we call endothelial cells. So the first thing that we have to pass are the endothelial cells. Now these endothelial cells rest on the basement membrane or the blood vessel. So that's the next thing that we have to pass, the basement membrane. And then from the basement membrane, so now the blood would have gone into this region, right, which is the space. Now we have to pass also the Bowman's capsule. The Bowman's capsule has got cells known as podocytes. Now podocytes have got processes, they have got foods, and they are going to be, let's say this is a podocyte, the podocytes will be leaving spaces, and those we call them slits. Now podocytes also rest on a basement membrane. So what will happen is that we are going to be able to pass the basement membrane where the podocytes are resting, and then also pass now the slits. So contents do not pass through the podocytes, but will pass through the foot processes or the openings or which are left by the podocytes. So the best one is this one. Does not pass through the podocytes themselves. How much of the filtered water is reabsorbed in the proximal tubule? How about which this one? Which one can you pick? One quarter, one third, one half, two thirds. One quarter. Okay, in the proximal convoluted tubule, 67% of water and salt is absorbed. So what you want to find out is what is 67% as a fraction. So 67 over 100. And this one is going to give you approximately 2 over 3. Think of it if this was like a scale, let's say 25 plus 25, that is a 50 plus 25. What is a 50 plus 25? That is a 75, right? So 67 is not very far away from 75. So approximately 67 over 100 is approximately 2 thirds. Okay, it's approximately 2 thirds because 1 quarter is 1 over 4, which is 25%. 1 third is 1 over 3, which is like, is it a 33%? 1 half is like a 50%. 2 thirds is 75%. So which one is near to 65%? So that is like a 2 thirds. So that's how much is going to be reabsorbed. The gold standard for estimating of glomerular filtration rate is the estimation of urinary clearance of. The clearance of which one of these compounds is going to be a gold standard? Which one can you pick? Inulin, creatine, urea, mannitol. Why? Oh, the best we can go for here is inulin. Okay, look at this. This is your Bowman's capsule, and then this one will continue like that. So, if you are talking about creatine, of course, creatine can be filtered, right? Can be filtered. And at the same time, this creatine can actually also be, there will be some creatine which can remain. What remains can be excreted. Okay, is that excreted or no? Is secreted? That's secreted. So meaning that all of it is going to pass at the end of it, or all of it can actually go out, and that is being excreted. So clearance is just a substance that is filtered but does not get reabsorbed. It does not go back. Nor is it secreted. It shouldn't come here. So inulin itself is good in that the in all the inulin can only be filtered here. Okay, can only be filtered. Meaning if you measure inulin that comes out of urine, it is measuring how much inulin was filtered. So you're actually measuring the glomerular filtration rate. But for some compounds like creatine, they can be filtered. At the same time, you are going to have some which are being secreted. Meaning that what you are finding in urine is not just explaining what is happening on the glomerular filtration. You're also talking about what is happening beyond the glomerular filtration. So it will not be accurate when measuring glomerular filtration rate. Does that make sense? Which of the following substances has a clearance ratio close to 1? Which one would you pick? Creatine, mannitol, urea, glucose? Yeah, creatine is going to have a clearance ratio which is close to 1. The most common acid-base disturbance in patients who are on mechanical ventilators is, remember the SWATEs here. Which one? On mechanical ventilators. Respiratory acidosis. Okay, respiratory alkalosis. Now, mechanical ventilators, think of those oxygens which they give, right? You are breathing using those. So what happens that they are actually supplying you with oxygen. They're supplying you with oxygen, meaning that you are going to be having a limited supply of what? Carbon dioxide. And it is carbon dioxide which causes acidosis. But they are supplying you with more oxygen, so meaning that you are going to go into alkalosis. Renin in the circulation originates mainly from macular denser juxtaglomerular cells, type 1 medullary interstitial cells, peritubular capillaries. Which one secretes renin? Yes, the the JG cells. So the juxtaglomerular apparatus itself, if you went, did you go through the video for anatomy? Mm, okay. Most of these questions came. Juxtaglomerular apparatus is going to be having macular denser cells. It's also having juxtaglomerular cells. It's also having mesangial cells. These are the three components of juxtaglomerular apparatus. This apparatus where absorption takes place. This is what we call the juxtaglomerular apparatus. Okay. 17. In the nephron, glucose reabsorption occurs mainly in the proximal tubule, loop of Henle, distal convoluted tubule, collecting duct. Which one do you go for here? Okay, so glucose, amino acids, lactate, in other words, nutrients are supposed to be all like 100% reabsorbed in the proximal convoluted tube. So don't expect to find glucose in urine because it's 100% reabsorbed. In the presence of vasopressin, most of the water filtered by the kidney is reabsorbed in the. Where do we reabsorb water when you have got vasopressin? Vasopressin is also known as ADH, antidiuretic hormone. Proximal tubules, thin descending limb, thick descending limb, collecting duct. Which one do you pick? Okay, so when you're talking about the renal tubules, for the renal tubules, as you go down from the proximal convoluted tubules and these others, these are going to be permeable to water. But then as you go up to the distal convoluted tubules and collecting ducts, those are not permeable to water, they're only permeable to ions. So the only way water can move out of this is when you have got ADH. So it is either the late distal convoluted tubules or the collecting ducts. This can only be permeable to water when you have got ADH vasopressin. What fraction of sodium is reabsorbed in the loop of Henle? 15, 25, 35, 5. Which one do you go for? Okay, so that is 25. The renal clearance of a substance is inversely related to urinary concentration. U. Clearance tends to fall at low urinary flow rates is directly related to its plasma concentration must fall in the presence of metabolic poisons. So clearance is given by urinary concentration. So this is the relationship of clearance. The concentration of that substance in urine multiplied by the concentration of that substance in plasma divided. Actually, U is going to be the concentration of the substance. Okay, and then V is going to be the urine flow rate, and then P is going to be the concentration of the substance now in plasma. Concentration in urine flow rate, concentration in plasma. So you can see clearance is not inversely related to U, it's directly related because it's on top. Okay, and then for B, clearance tends to fall at low urinary flow rates. You can see flow rate is on top, so it can't fall. It is directly related to the plasma concentration. You can see it is in the denominator, so it is inversely related. So if A is wrong, it's inversely related to urinary concentration, and these other ones are wrong. You don't have a choice but to remain with this one. Must fall in the presence of metabolic poisons. As plasma glucose concentration rises above the normal, glucose. So when plasma glucose is rising above normal, what happens that if you have got too much glucose, now you know that glucose is normally stored, but if the glucose in blood rises too much beyond normal, the excess can be excreted. Now A is saying transport maximum increases linearly. What happens is this: glucose is going to be stored. Okay, glucose is going to be stored, but now for glucose to be stored, it's transported to where it is supposed to be stored, but it is not transported by diffusion, it is by facilitated diffusion. It passes through channels, so it has got actually transporters. Okay, so if those transporters are there, they are empty. When you increase the concentration of glucose, Also, the rate at which you are storing it will increase. But there will be a point whereby all the channels have been filled up such that even if you increase the concentration, the rate of storage of glucose is not increasing. So transport maximum is going, of course, increase linearly, but there's going to be a point when it can no longer. Transport maximum is the maximum point here, where the concentration can no longer affect the rate. So it does not even increase linearly there, unless if we said rate, not transport maximum. And then clearance is going to increase linearly. Okay, let me put a dot there. Reabsorption increases and then levels off. So what happens is glucose, because it is more in blood, some of it, what will happen is this, in the renal corpuscle, draw it like that. Remember, it is high in the blood, right? So when it was removed, it came here. That is filtration. And then now some of it will start going back. And that is known as reabsorption. So it will start being reabsorbed. But because there's already much in the blood, it will be reabsorbed and then it will stop. Okay, so reabsorption is going to increase and then it's going to be able to level off. So hope that makes sense. 22. A substance is being secreted by the renal tubule if what is to be secreted? To be secreted means being removed from here, going into the renal tubules. That's secretion. Because going back into blood, that is reabsorption. So the only way a compound can come from blood to the renal tubules is if it is high in blood and then low in the renal tubules. About clearance rate being greater than 250, this one, let me put a dash. Excretion rate is increased by tubular enzyme poison. Excretion rate is increased. Okay, what did we say about the poisons here? Clearance of a substance must fall in the presence of poison. So poison drops clearance. So meaning this one, excretion is going to be increased, meaning that can't be true because excretion is as a result of clearance, things which have been removed from blood. So it can't increase with poison. Instead, it's supposed to decrease, right? So this one can't be true. And then C, concentration rises along the proximal convoluted tubules. D, concentration in urine is greater than in plasma. Now, concentration in urine, if it is greater than in plasma, secretion can't happen. Okay, instead, reabsorption is the one which is going to happen. Concentration in urine should be less than in plasma for something to be secreted. So what we remain with is C. Concentration rises along the proximal convoluted tubule. And this is what happens. You have got what you call the countercurrent multiplier. So as you get to go down, concentration in the proximal tubules is going to be increasing as you go down. On top you start with a 300, as you are going down is going until you reach the loop of anywhere you reach maximum of 1200. In the nephron, the osmolarity of fluid in the nephron, the osmolarity in the fluid in the A tip or the loop of Henle is less than plasma. Now, tip or the loop of Henle is 1, 2, and plasma is 300. So, meaning this statement is not true. Bowman's capsule is less than that in the distal tubules. In the Bowman's capsule, the concentration is around 300. And then at the end, in the distal convoluted tubules, the concentration is supposed to be also the same. So meaning this statement is not true. If at all actually in the distal tubules the concentration will reach even up to 200, meaning that it's supposed to be less in the distal tubules. Okay, and then collecting duct rises when vasopressin is being secreted. What is the effect of vasopressin? Vasopressin causes water reabsorption, meaning that water is being removed from the collecting duct to the blood. So because water is being removed from the collecting ducts, what's happening to the concentration when water is little? Concentration rises. So collecting duct rises. Okay. Osmolarity does rise, yes, in the presence of vasopressin. Proximal convoluted tubule rises along its length. Now, this statement, we're supposed to tick it on top. We had ticked it, but then for this one, it can definitely the best here would be C. The concentration along, of course, the proximal tubules is going to be now this in the nephron. The osmolarity of fluid in the proximal convoluted tubules rises along its length. As you go down, the concentration is going to be rising from 300 to 500 to going like that, but rises along its length. The along its length, we don't know if it's talking about along going downwards or upwards. Anyway, not that specific, but the best we can pick is that one. Transport maximum limited reabsorption of a substance implies that it's now, as we already said, transport maximum is a point where you can no longer, the rate no longer increases when you increase the concentration. Reabsorption is passive. About transport maximum, it means that reabsorption is not passive. It doesn't just happen like that. And then reabsorption is critically related to tubular transient time. It's not really, transport maximum does not talk about time. It relates reabsorption to concentration. Reabsorption is complete below a certain threshold load. This is true. Okay. Reabsorption is going to finish below a threshold. Below this point, reabsorption has already finished. That's that even when you increase the concentration, you can no longer reabsorb that compound because reabsorption has finished. Remember, reabsorption is you are trying to take something that is in the renal tubules back into blood. But if it is already enough in the blood, even if you increase the concentration of that compound in urine, it can no longer go back into blood because it's already enough in blood. So it is just going to be excreted. Okay. Renal clearance falls with its plasma concentration. Renal clearance falls with its plasma concentration. This one I'm going to put a question mark. But of course, normally what happens is that if a substance is less in blood, even its clearance, the way it's going to be released in the Bowman's capsule is going to be less because it is less in blood. So don't expect it to be more excreted. But we want what is very best here. So the best we can pick is going to be C. Because transport maximum itself is about reabsorption and concentration. Potassium A is actively secreted in the distal convoluted tubule. B is reabsorbed in the proximal convoluted tubule. C, excretion is determined largely by potassium intake. D, or the above. Which one would you pick here? Is actively secreted in the distal tube convoluted tubule. This one is true, yes. In the distal tubules, you can only secrete potassium in the presence of sodium, so it uses energy. But it is also reabsorbed in the proximal convoluted tubules. In the proximal convoluted tubules, almost everything is reabsorbed. Excretion is determined by largely potassium intake. This is also true. The more you take in potassium, the more you are going to excrete it. So meaning that it's all of the above. Secretion of renin A occurs in the stomach during infancy. B is stimulated by the hormone angiotensin 1. C is stimulated by F4 in extracellular fluid volume. And D inhibits ACTH secretion by the pituitary gland. How about this one? Which one would you pick? C? Okay. B, stimulated by the hormone angiotensin 1. Now, what happens is that renin will convert angiotensinogen into angiotensin 1. So, meaning that it's not angiotensin 1 which is affecting the secretion of renin. So, what happens is that when there is low blood pressure, low BP, okay, low BP is going to cause the secretion of renin. Apart from low BP, look at this. Also, F4 in fluid. Because if fluid volume falls, it means that there's going to be low blood pressure. So a fall in extracellular fluid volume, if there is a fall in blood volume, that also stimulates the production of or the secretion of renin. Okay, so number 27, in chronic renal failure, glomerular filtration rate falls by 70% before the conditions gives rise to symptoms. Blood partial pressure of carbon dioxide tends to be low. Anemia is common, or the above. Which one would you pick for this one? Partial pressure of carbon dioxide tends to be low. Okay. So what happens in chronic renal failure? In chronic renal failure, the kidney is not working well. Since the kidney is not working well, it means that it has affected the reabsorption and the other processes that happen in the kidney, right? So because it can't work well, it means that it affects the way things are going to move into to be excreted. So even the hydrogen ions will not be excreted. So there's going to be an increase of hydrogen in the blood because the kidney is not working well to remove that hydrogen. And that leads to metabolic acidosis because there's a problem with the kidney. Now, what the body wants to do is it wants to compensate for the metabolic acidosis. So it wants to reduce the amount of hydrogen that will come from respiration. So because of that, what happens is that you are going to be breathing very much fast so that you can excrete more carbon dioxide. You want to excrete more carbon dioxide. So what happens is that blood carbon dioxide is going to be low because carbon dioxide, if it is more in blood, it will cause more hydrogens, and that is what you don't want. So because of that, you have got more carbon dioxide being excreted. What is that going to cause? It is going to result in another condition. Okay, you are going to have low carbon dioxide, meaning that you are now going to result into respiratory there is a respiratory composition, so that will be respiratory alkalosis now resulting. Now, after that, look at option A, glomerular filtration rate may fall. There's going to be a fall in glomerular filtration rate because the kidney is not working well. Another thing, because the kidney is not working well, you're also going to have anemia. Why is it like that? Anemia is a low red blood cell count. And how is it related to the kidney? Remember, we talked about the juxtaglomerular apparatus. It's made up of the juxtaglomerular cells, which are going to be involved in the production of renin. Also made up of macular denser cells, which are involved in regulating salt levels. You also have the messenger cells, which are involved in the production of erythropoietin. And erythropoietin is necessary in the formation of red blood cells. So if the kidney is not well functional, it will affect the production of erythropoietin, to affect the production of red blood cells, and that leads to anemia. So this means that all of the above. 28. Diabetes insipidus, which is a deficiency of ADH, causes a fall in the. Now you know that ADH is necessary in the bringing of water from urine into blood. Meaning that if you don't have ADH, you're going to have more water in urine. So diabetes insipidus causes fall in the osmolarity of the urine. This is going to be true because you are not removing water from the urine, so the osmolarity is going to fall. Reabsorption of water from the proximal tubules. Now, ADH doesn't affect proximal tubules, it affects the late distal tubules and the collecting ducts. Extracellular but not intracellular fluid volume causes a fall in extracellular fluid but not intracellular fluid volume. Okay, not necessarily true. It is affecting water. Okay, it's affecting water. Water can no longer move from the tubules into blood. So what happens that the concentration in the blood is actually increasing because you're not having water there, right? And so that will affect water will start moving from the cells going into ECF. So it's going to cause not a fall in ECF, but you're expecting it to this relationship here. There's going to be an increase in ECF and a decrease in ICF because you don't have enough water coming from the urine into ICF. So there's actually going to be a fall also in intracellular fluid. And then extracellular fluid, the osmolarity, it will not fall. It will actually increase as we have said. 29. The cystometrogram shows. Now, the cystometrogram is a graph that will show how functional the bladder is. So it is going to be showing here is going to be showing the pressure generated in the bladder when there is an increase in volume in the bladder. So normally when the volume in the bladder starts to increase, the pressure in the bladder is going to be also increasing. And when you reach somewhere 50 mils of fluid in the bladder, the pressure no longer be increasing such that even when the volume in the bladder increases, there is no pressure that is increasing. But when you reach somewhere which is somewhere 1,000 or 500, at this point, if you increase any more the volume in the bladder, there's going to be a pressure increase. So meaning that someone wants to urinate. But as that is happening, there's going to be like some kind of pressures being generated with each increase. But those pressures are increasing and dropping. So and you can see they are becoming higher and higher like that. What does that mean? It means that when volume in the bladder increases, the pressure is going to increase. You want like you feel like urinating, but after a time you stop feeling like urinating. If it increases more, the force will again increase more. You want to feel like urinating, but it will stop. But there'll be a point after you've exceeded like the 500, which is the normal capacity of the bladder, where the pressure in the bladder will increase such that you just want to urinate and it can't go back down. So this is the cytometrogram. So looking at A, little rise in pressure with, with rise in volume at low bladder volumes. Little rise in pressure with rise in volume. That is what is happening at low bladder volumes. You can see at low bladder volumes, that is what is happening, right? So this statement is true. A steep rise in pressure when volume rises above 100. You can see above 100, there is no any steep rise in pressure there. The pressure is actually constant. And then for C, females generate higher pressure during menstruation than males, necessarily not relating to the cytometrogram. Patients with chronic injury, I mean, patients with chronic urinary tract obstruction can generate than normal obstruction, lower than normal menstruation pressures. Really not. If someone has got a problem with the kidney, that really doesn't mean that they're going to generate low menstruation pressures, that pressure to feel like weeing. As long as urine has reached the bladder, because this scale is telling us not about the kidney itself at that point, but it's telling us about the bladder, the problem with the bladder. But of course, it does relate to how excretion is happening, but really not to be true like that for this statement. The patient with chronic urinary tract obstruction can generate lower menstruation pressures. The pressures will be the same. If you have got that bladder filled, you still feel like urinating. Number 30. The term filtration fraction refers to. Now, the fraction of what has been filtered is filtration fraction. Will talk about how much has been filtered divided by how much went to the kidney. That is the renal plasma flow. So it's the glomerular filtration rate, how much has been filtered on the glomerulus, divided by how much went to the glomerulus. So that is going to be B. Third one, in plasma, the half-life of, so we're comparing the half-life of thyroxine. Thyroxine is T4 with adrenaline. We're also comparing thyroxine with triiodothyroxine, triiodothyronine, and that is T3. Also comparing noradrenaline with acetylcholine. Now the half-life of thyroxine T4 is around 6 to 7 days. Okay, if you can't sit, just try to log out and then log in. I think it's just your connection. So 6 to 7 days. Now half-life is just telling us about the time it takes when this hormone is in the blood for it to reduce to half. That's half-life. And then the half-life of adrenaline is just around 2 to 3. This one is in minutes. Half-life of T3 is around 2.5 days. And then for no adrenaline is just around 2 minutes. And then acetylcholine, its half-life is just a matter of milliseconds. So within a few seconds in blood, its concentration is going to reduce to half. So now let's look at this. Half-life of thyroxine is longer than that of adrenaline. You can see thyroxine is the highest, so this is true. Thyroxine is longer than that of triiodothyronine. This is also true. No adrenaline is longer than acetylcholine. Acetylcholine has a smallest half-life, so that is also true. So it is all of the above. 32. During sleep, there is a fall in the circulating levels of. In case you cannot really see, make sure that you have got at least enough bundles. During sleep, there is a fall in the circulating levels of cortisol, insulin, adrenaline. Now you know that these guys, adrenaline is produced when you are running or when you're under pressure like that. Insulin is produced when you have eaten. Now when you're sleeping, you have not eaten. Cortisol when you are like, you know, pressured in that way. So now when you are asleep, you expect all these to fall because you are not that active metabolically. So that should be D. Adrenocorticotropic hormone, ACTH, secretion increases when the medium eminence of the hypothalamus is stimulated, when aldosterone blood levels fall, when cortisol blood levels fall. A and C. Which one can you pick for this one? Okay, you would pick A when the median eminence of the hypothalamus is stimulated. So ACT, adrenocorticotropin hormone, will come from the paravertebral nucleus. So what happens that the paravertebral nucleus now, where is the paravertebral nucleus located? The paravertebral nucleus is located in the posterior pituitary, not anterior but posterior. Okay. So what happens is that paravertebral nucleus is going to release corticotropin releasing hormone, and the corticotropin releasing hormone will be able to circulate into blood, and then from there is going to be able to break something which is known as the pro-opiomelanocorticotropin, and then it will form the adrenocorticotropin hormone. So that was from, remember from where? From the posterior. Actually, every time we're talking about blood circulation, the only portion where you have got the anterior pituitary. Let me ask this question: between the anterior pituitary and the posterior pituitary, which one is nervous? I mean, which one has got neural tissue? Which one has got neural tissue? Or what's the other name for anterior pituitary and posterior pituitary? Adeno hypothesis, yes. And then the other one. So the posterior pituitary is neural hypothesis. meaning that it is related, it has got neural tissue. The anterior is the adenohypothesis, which has got like, it is not, it is independent, it's different from the posterior, which is actually part of the hypothalamus. Okay. So for A, when the median eminence of the hypothalamus is stimulated, this is true because posterior pituitary, where ACTH is secreted from, is related to the hypothalamus. Now, what is the function of this same ACTH when it is produced? Any function that you know? Any function that you know for the ACTH? Cortisol. Okay. So, option B is saying when aldosterone blood levels fall. Now, what causes the production of aldosterone? Remember, aldosterone is related to F4 in what? Aldosterone is going to be produced when, what is the function of aldosterone in the, we are just talking about the renal circulation here. Aldosterone. ADH is related to water reabsorption. How about aldosterone? Yes, the sodium reabsorption. So this one is related to salt reabsorption. So, and to be specific, this one, because we are revising, so we, this is the time we can talk about these things. Which part is aldosterone produced from? Aldosterone is going to come from the adrenal gland, but specifically where in the adrenal gland? So the adrenal gland has got the medulla and the cortex. The cortex has got the zona glomerulosa, fasciculata, reticularis. Be specific, the zona glomerulosa is where aldosterone is going to come from. Remember salt, sugar, sex, that mnemonic they give. Okay. So the paravertebral nucleus in the hypothalamus will be able to secrete corticotropin releasing hormone, and that one is going to act on the, it actually acts on the anterior pituitary. Oh, so this one had even, we had said that the when it worked on the anterior pituitary to produce ACTH. Now, ACTH I had mentioned earlier to say that it's going to be released into blood circulation. What is related to blood circulation is not the posterior pituitary. Posterior pituitary things will be produced from the hypothalamus, they'll go direct into the posterior pituitary. But the anterior pituitary, when things are produced, they'll actually go into blood circulation. So this statement can't be true here about the median eminence of the hypothalamus. What is related to the hypothalamus is not related to blood circulation. Hope you get that. So from the anterior pituitary is going to be able to release the same adrenocorticotropin hormone. Now this one is going to go and act on the zona glomerulosa, and that is now going to cause the release of aldosterone. Okay. So ACTH is necessary in aldosterone release. So when aldosterone blood levels fall, ACTH is going to be produced. Now, another question should be, where is cortisol? So we've talked about the zona glomerulosa. What comes out of the zona fasciculata in that case? So zona fasciculata is going to be the one where cortisol comes from. And then the zona reticularis, you are going to have androgens. Now, zona fasciculata, what will happen is that the paravertebral nucleus again is going to secrete the same uh, corticotropin releasing hormone which produces ACTH. ACTH will also stimulate the zona fasciculata, and that is going to make sure that cortisol is produced. So when blood levels of cortisol are low, there's also going to be the secretion of ACTH. Now I can see B and C are also correct. And then for A, when the median eminence of the hypothalamus is stimulated. Wow. So I don't even know now the best one that we can pick here. But ACTH is going to cause, it does act on the adrenal gland to cause the production of things which come from the adrenal gland. And that includes cortisol, aldosterone, and also androgens. And you can see these two are not together. Aldosterone blood levels fall, and cortisol blood levels fall. They are not together. So that will be now a debate that you are going to suffer to be able to remove, to choose which one you're going to choose. Unless maybe if it was true or false, you would say true, true, and then false. Melatonin A is produced mainly in the intermediate lobe of the pituitary gland, synthesized in the body from serotonin. Blood levels are higher during the night. B and C. Which one would you pick for this one? Okay. So melatonin is a hormone that is produced to regulate the night and day cycle. If it is produced, someone gets to feel that sleepy. It's actually produced from serotonin. Yes. Okay. So the answer is B and C. Thyroid hormone, when secreted in excess, may cause an increase in the thyroid hormone when secreted in excess. A. Frequency of defecation. B. Energy expenditure required for a given workload. C. Heat rate when cardiac adrenergic and cholinergic receptors are blocked. Now, I didn't include one option here, option D. So, I can't even answer it because the correct answer I wrote was actually option D. Which of the following hormones is not a glycoprotein? Which one is not a glycoprotein? Thyroid releasing hormone, follicle stimulating hormone, luteinizing hormone, all the above. Which one can you pick? Which one can you pick? Is not a glycoprotein. Okay. Now, when you're talking about types of hormones, they will be classified depending on what make them. For example, I've got peptide hormones, steroid hormones. Peptide hormones include luteinizing hormone, follicle stimulating hormone, growth hormone, glycogen, insulin, ADH, and also parathyroid hormone. Steroid hormones, those which are made up of lipids, include testosterone, estrogen, progesterone, aldosterone, cortisol, gonadotropin, thyroxine. So glycoprotein, which one of is not a glycoprotein? So 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 TRH, that is a thyroid releasing hormone. This guy is a peptide hormone. Follicle stimulating hormone is also a peptide hormone. Okay. Luteinizing hormone is also a peptide hormone. So which one is not a glycoprotein? So it's all of the above. That's what we can pick. Okay, because all of these are peptide hormones. Aldosterone secretion is increased by an increase in plasma volume, osmolarity, ACTH concentration, ADH concentration. Which one would you pick? Which one would increase the secretion of which one would increase secretion of aldosterone? Okay, the thing, what is the function of aldosterone? So it is involved in sodium reabsorption, right? Sodium reabsorption. And you want to reabsorb sodium if, look at this, you want sodium to go back into blood. Why should sodium go back into blood? It means you want to increase the concentration of sodium in blood. Why should you increase the concentration of sodium in blood? It means that the concentration of sodium in blood is low. So if there's increase in osmolarity, you don't expect to have aldosterone because aldosterone wants to increase osmolarity. But if there is an increase in volume, if you have got more blood, okay, you have got more liquid, you want to absorb more salt, okay, you want to have more salt in order to have more, think of it like you have got more water, so you want to add more salt to it. So if there's an increase in volume, that is going to be true. Of course, ACTH concentration also causes the production or the it causes volume to I mean aldosterone to be released, as we already mentioned, because it does act on the adrenal gland, but the best we got there for is volume. Page 7, which is not correct regarding growth hormone, promotes positive nitrogen and phosphorus balance. Sea levels in the blood are higher in children than adults. Secretion surges during sleep. Stimulates the liver to secrete somatomedins, which regulate bone and cartilage growth. Which one can you pick? So remember, growth hormone is there for growth. So it will stimulate the liver to produce somatomedins, which regulate bone and cartilage growth. The main thing is growth there. 38. When secretory activity of the thyroid gland increases, the gland takes up iodide from the blood at a faster rate. You expect that. Remember, the thyroid gland uses iodine to make its thyroxine D. That stimulates the liver to secrete somatomedins. So the thyroid gland releases thyroid hormone, which is made up of T3 and T4, and there tyrosine is necessary, iodine is also necessary. So if the activity of thyroxine is supposed to increase, the gland is supposed to take up more iodine, meaning that option A is correct. Follicular cells become more columnar. So the thyroid cells will become more columnar because now they are being more active. Follicular cells ingest colloid by endocytosis. So the best answer will be D for this one. Okay. Are we good? At 9, which is not correct regarding releasing hormone produced by the hypothalamus. Is not true. Are secreted by cells in the median eminence, pass down nerve axons to reach the pituitary gland, may control the output of more than one pituitary hormone. C is correct. For example, you talk about, let's say, thyroid releasing hormone. If it is produced, it acts on the hypothalamus to produce thyroid stimulating hormone, and it actually what will be produced from the hypothalamus will act on the pituitary gland, and it will be producing more things. So may control the output of more than one pituitary hormone. C is correct. Regulates the release of thyrotropin. That is also correct. Uh, Pass down nerve axons to reach the pituitary gland. Of course, that is also correct. Okay, but not all hormones. Look at which is not correct regarding releasing hormone produced in the hypothalamus. Not all hormones from the hypothalamus are going to be passed down axons to reach the pituitary gland. Not all of them. It's just those which are on the posterior pituitary, because others will reach the pituitary gland via blood. So meaning B will not be really the best answer because it is too general. Okay. And then question 40. Thyroid stimulating hormone secretion is increased. Thyroid stimulating hormone secretion is increased after total removal of the thyroid gland in infants born without thyroid gland when metabolic rate falls in starvation. Which one would you pick for this one? Thyroid stimulating hormone. When should its secretion increase? When metabolic rate falls. Okay. And then there's also B, in infants born without thyroid gland. Okay. So in the when you're talking about the thyroid stimulating hormone, so first what you are going to have is you are going to have the paravertebral nucleus of the hypothalamus. The paravertebral nucleus is going to release thyrotropin releasing hormone, and this one is going to circulate in blood. Okay, it will be able to circulate in blood, and then it will go and stimulate the hypothalamus to secrete thyroid stimulating hormone. Thyroid stimulating hormone is now going to go to the thyroid gland and act on its receptors, and then it will cause it to produce the thyroid hormone. Now the question should be, why do you need the thyroid hormone? Thyroid hormone has got a lot of target organs, including the liver. So it will go to the liver to make sure that uh, glycogen the breakdown of glycogen happens. Why the breakdown of glycogen? Because you need to have more glucose. So that is one effect. Take note. You can also go to the heart to make sure that it increases the cardiac output of the heart. You can go to the central nervous system to just make sure that there is increased myelination and all those things, because you are increasing activity of the body. It will also go to the bone to make sure that there is an increase. So the first regulation of osteoclast activity, the breaking of bones, and also to stimulate growth of bones, to go also to adipose tissue to break down triglycerides so that you can have more glucose being formed. Same, it will go to the muscles to stimulate the breakdown, to stimulate activities in the muscle. Okay. So in other words, you are just increasing metabolic activity. So thyroid stimulating hormone is produced in the pituitary gland so that it can act on the thyroid gland. So for A, after total removal of the thyroid gland, we don't expect that to increase thyroid stimulating hormone. And B, infants born without the thyroid gland, we don't expect that to increase thyroid stimulating hormone. Then for C, when metabolic rate falls, now the thyroid stimulating hormone is produced to increase metabolic rate. And then in starvation, so between C and D, which one would you pick between C and D? Remember, the aim of thyroid stimulating hormone is you want to increase metabolic rate. Would go with what? With the C. Okay. Okay. So we want to make sure that we increase metabolic rate. That's why we are doing whatever that we can. We are going to the adipose tissue and making sure that we remove fat there to convert it to glycogen. And then we're also converting glycogen to Okay, sorry for that. Are you able to get me? Someone called me, that's why. Okay, so we are saying that the aim of thyroid stimulating hormone is to increase metabolic rate. So when metabolic rate falls, you expect it to, you want to increase it, right? So we can pick C. So, and then question 41, which statement is not correct regarding the pituitary gland? Output prolactin is regulated by hypothalamic releasing factor, secretes antidiuretic hormone when blood osmolarity falls. C. For the previous one, we'll go for C. Okay. Which statement is not correct regarding the pituitary gland? A. Output of prolactin is regulated by hypothalamic releasing factors. For you to release prolactin, you need what is coming from the pituitary gland, so you expect that statement to be true. Secrete antidiuretic hormone when blood osmolarity falls. Now, HDH is not secreted from the from the pituitary gland, right? Pituitary gland just stimulates the adrenal gland to produce ADH. So that statement is not true. For C, as an intermediate lobe, which secretes melanotropin, so that should be true. Responds to nervous and hormonal influence from the brain. That is also true. We know that it responds to the hypothalamus. So the answer is B. Which statement is not correct regarding the thyroid gland? Takes up iodine against electrochemical gradient. We want what is not true. Okay, takes up iodine against its electrochemical gradient. That is true. When iodine is high in blood, to be taken to the thyroid gland against its gradient, so as to decrease in size when the dietary iodine is deficient. That is not true. For the fact that you have not eaten things without iodine doesn't mean that it will decrease in size. Contains enzymes which iodinize iodine to iodide. That is true in the formation of the thyroid hormone. You need those hormones to be able to convert iodide to iodine. We'll talk about the process. And then T contains enzymes which iodinate tyrosine. That is also true to tyrosine. We need to add tyrosine to add iodine so that we can form the thyroid hormone. So the answer is B. 43. Growth hormone secretion increases when the blood glucose levels fall as a lactogenic effect increases the size of viscera. I didn't include option D. So increases when blood glucose levels fall as a lactogenic effect increases the size of viscera. Okay, I don't know what option D was saying, but when growth hormone is released, you expect it to. Okay, let me maybe make us get to speak a bit. What is the effect of growth hormone on the body? What is the effect of growth hormone? No one. So growth hormone is going to be released, and what triggers its release is when you have got a lot of amino acids in the body, and then also when you have got low glucose in the body. Now, when you have got low glucose in the body, it's going to be a negative trigger, meaning that it will reduce the production of growth hormone. When you have got high levels of fat, it will increase. Right? Actually, low glucose it's not a negative trigger but a positive trigger. Low glucose, high amino acids, high fats, exercise, stress, those are going to trigger growth hormone to be produced. What reduces the production of growth hormone is somatostatin, obesity, hyperglycemia, meaning when you have got what is hyperglycemia is when you have got high glucose, right? Also high glucose will be a negative effect on growth hormone. Pregnancy also somatomedins. So what is the answer here then? It will increase when blood glucose levels fail. That answer is correct, right? So that is true. Question 53. Description of the term neurohormone is applied to oxytocin and vasopressin, nitric oxide and carbon monoxide, glycine and glutamate, follicle stimulating hormone and luteinizing hormone. Which one would you pick for this one? So neurohormones will refer to oxytocin and vasopressin. These guys produced from from the hypothalamus. Growth hormone secretion is increased by all of the following except this one you can answer because I've already even mentioned it. Which one will not increase growth hormone secretion? Pharmacological dose, hypoglycemia, exercise, protein meal. Which one would you pick? Okay, hypoglycemia, that's correct because it increases. Iodine is concentrated in the thyroid follicular epithelial cells by Iodine is concentrated in thyroid follicular epithelial cells by primary active transport, secondary active transport, simple diffusion, facilitated diffusion. Now, the movement of iodine is going to be by secondary active transport. You are transporting one compound while you're also transporting the same iodine. Epiphyseal closure in human is mediated by androgens, estrogen, somatomedins T3, epiphyseal closure. So the closure of the epiphyseal plate is going to be associated with the estrogen. So meaning if you have got more estrogen, expect that growth should be limited. Men castrated before puberty grows taller because release of growth hormone is increased, of androgen resistance, estradiol level in the epiphyseal growth plate takes longer to reach its threshold, of insensitivity to IGF-1. Which one would you pick for this one? Which one would you pick? Just a moment. Okay. So men which are castrated from birth, why do they grow taller? So for a person that is castrated where the penis is cut from birth, what happens is that there is low levels of testosterone in the body. Because there is low testosterone assists in the fusion of the epiphyseal plate or the closure of the epiphyseal plate. So because it's not there, it means that the epiphyseal plate will not be able to close, and so it will take longer for the epiphyseal plate to be able to close and the person grows taller. Okay. So Release of growth hormone is increased, androgen resistance, estrogen levels in the physical plate takes longer to reach its threshold. So the answer is going to be C. Okay. Estradiol levels in the physical plate takes longer to reach its threshold, which can close the epiphyseal plate. Removal of the thyroid gland without replacement therapy leads to an increase in the following, except if you remove the thyroid gland: blood TSH level, blood cholesterol level, blood glucose level during an oral glucose tolerance test, response time for tendon reflex. Which one would you pick? So when you remove the thyroid gland and you don't replace it, it's going to lead to an increase in the following, except, so look at, say, blood glucose levels during an oral glucose tolerance. Remember what blood glucose, if you increase blood glucose, what does it do to, okay, I want to talk about growth hormone. Is this not growth hormone? Removal of the thyroid, if you remove the thyroid gland, to it will lead to an increase in the following: blood TSH levels. Now TSH, thyroid stimulate, thi- is it thyroid stimulating hormone or thyrotropin stimulate, thyroid stimulating hormone? And then blood cholesterol levels, and then D, response time for tendon reflex, blood glucose levels during an oral glucose tolerance. Okay, the function of the thyroid gland, as we've talked about, the thyroid gland, you want to make the thyroid hormone, and thyroid hormone, which has got a lot of functions in the body, right? We've talked about different ones, basically increasing the metabolic rate in the body. So when you remove the thyroid gland, it will not be able to increase blood glucose levels in the body. It does not increase any blood glucose in the body. When you get to take glucose, this is blood glucose levels during an oral, you take glucose by mouth, so it will not be able to increase it if you remove the thyroid gland. But it can increase, if you remove the thyroid gland, you can have an increased TSH levels, because TSH is not produced from the thyroid gland. So even if it's not there, it can actually be produced and it will be high. Blood cholesterol levels can still be high in the body even if you don't have the thyroid gland. Okay, so blood glucose levels will not be increased. 59. A pituitary tumor secreting excess growth hormone in adults leads to a homonymous hemionopia, gingitism, reduced levels of somatomedins in blood, raised blood glucose levels. How about this one? Which one would you go for? Which one would you pick? No answer? Which one? We're almost done. C. So imagine there is a tumor on the pituitary gland and then there is excess growth hormone being produced. What do you expect? Homonymous hemionopia, gingitism, reduced levels of somatomedins in blood, a raised blood glucose level. Which one would you go for? reduced levels of somatomedins, reduced levels of somatomedins. Why would you go for C? Okay, so remember growth hormone is inhibited by a lot of things. It's inhibited by somatostatin. Somatomedins also inhibit it, right? You also have obesity inhibiting it, low glucose inhibits it. So when you have got high excess growth hormone, that would mean what inhibits it should be low. Somatomedins should be low, somatostatin, obesity, low glucose. So you don't expect to have raised glucose but low. Would have expected, we expect also the person to be big, but gingatism is not caused by excess growth hormone in adults but in children. So that's why big couldn't be the answer. And then the hemianopia. Hemianopia is just where there is loss of visual. So really you don't expect to have loss of visuals because of growth hormone. Okay, so the best answer you can pick C. Number 60. Impaired growth hormone secretion. Impaired growth hormone secretion in children causes delayed puberty. In children leads to short stature with more stunting of the limbs and the trunk. It's associated with a pale, fine, and soft skin. In adults leads to a reduction in the size of the viscera. How about this one? Which one would you pick? So if you don't have enough growth hormone in children, you expect the children to grow. They're going to have a short stature, so it's B. Growth hormone, growth hormone of the following except. I don't know what this question is saying, but we had already answered it. I just typed it wrongly. It's one of those questions on top. Okay, and then section B. After some few minutes of an intravenous injection of a small amount of PAR into a human subject, we've been told that the following values were measured. The concentration of PAR in blood was found to be 14 milligrams per mil, and then V, which is the plasma. What does V represent? That is the renal, the blood, the rate. Is the flow rate. Okay, flow rate of the blood, and then you also been given the concentration of PAR in plasma. Calculate renal plasma flow. How do you calculate renal plasma flow? Anyone to help? Renal plasma flow. Tatuishive. Yandika. Renal plasma flow is given by the concentration of the compound in urine times the urine uh, flow rate divided by the concentration of that compound in plasma. This is what also will give you this is what gives you the clearance rate. Okay, so U is 14 times V, which is what is the value for V, that is 0.9, divided by P, which is 0.02. If you have a calculator, you can help punching there. So you can also look at the units. U is in milligrams per mil times V is in mils per minute. So meaning that mil and mil cancel out. And then we are saying divided by, which is the same as times plasma concentration is mils per milligram per mil. So the mil will go on top, with milligram down. So milligram will cancel with milligram. So the answer is going to be in mils per minute. That is the renal plasma flow. Okay. The answer that you get. 630. Okay. And then the next question is saying what percentage of the body's blood flow to the kidney? What percentage of the body's blood flow do the kidneys receive? Now you know that the kidneys receive 25% of the blood that flows, right? The kidneys receive 25% of the blood that is received. What does that mean? So of the total blood which is going to the kid from the heart, that is renal blood flow. 25% is going to the kidney. So that is 25% of how much is going to the kidney. So now how much blood goes to the kidney? You've been also told that packed cell volume. Packed cell volume is representing what? The amount of, if you get blood, how much of that blood is red blood cells? But we know that 25% of all the blood that goes to the of all the blood that comes from the heart goes to the kidney. Renal blood flow. Now, renal plasma flow is actually equal to renal blood flow multiplied by 1 minus hematocrit. That's why we are even given hematocrit there. It wasn't for formality. So what percentage of the body's blood? So we want the renal blood flow. Renal blood flow is going to be equal to the renal plasma flow, and we calculate the renal plasma flow as 630 divided by 1 minus hematocrit. 1 minus hematocrit is 0.45. So the answer that you get here will be the renal plasma, renal blood flow. Is that okay? A 35-year-old woman comes to your clinic complaining of impending feeling of anxiousness, palpitations, and you make diagnosis of hyperthyroidism. What will be the effect? What will be the difference between the primary and secondary hyperthyroidism in terms of increase, normal, or decrease? We're talking about thyroid stimulating hormone T3 and T4. Now, primary hypothyroidism means that the problem is on top, like from the pituitary there. Secondary hyperthyroidism means that the problem is on the thyroid gland, okay, where the thyroid hormone is supposed to be produced. Now, when you're talking about it being either primary, secondary, and those you are comparing the levels of these guys, starting with the primary one, the primary hyperthyroidism. Now, primary hyperthyroidism, I've even swapped them actually. Primary is a problem with the gland, right? Secondary is a problem with the pituitary gland. So, in primary hyperthyroidism, can be caused by a lot of things. Okay, T3 and T4, you expect them to be high, and then thyroid stimulating hormone is going to be low. Okay, the problem, remember, is with what? Problem is with the gland itself. So TSH is low, while T3 and T4 are high. And then for secondary hyperthyroidism, the problem is on the pituitary gland there. So there is going to be, remember this is hyperthyroidism, meaning that we are producing thyroid gland hormone too much. So for primary, since the problem is with the gland itself, so we are producing too much, the gland is producing too much. The gland is what produces T3 and T4, those are high. Now the the pituitary gland is just producing normal TSH, so the TSH is low. But for secondary, where the problem is on the pituitary itself, so what is going to be high, you are going to have thyroid stimulating hormone being high, thyroid releasing hormone also being high. Because of that, it is also going to produce high T3 and T4, so everything ends up becoming high. Okay, and the thyroid cells will become overreactive. So the problem here is can be much high in females than it can be in males. Thyroid hormone synthesis involves the following steps: thyroid hormone secretion, iodine trapping, condensation, storage, thyroglobulin formation, iodination, iodine, iodination, iodide. Now I want to list these steps in order in the biosynthesis. Now first thing first, you are going to first form iodine. So the first step will be formation of iodine. Okay, so which one is that? Thyroid hormone secretion, iodine trapping, condensation, storage, thyroglobulin formation, iodination. Okay, so you are going to first form iodine formation, and then you are going to now have thyroglobulin formation. After you form your thyroglobulin, now you are going to have iodination. When you do the iodination, now you can get that iodine, you now couple it on the thyroglobulin, so that will be condensation, also known as coupling. And then you are going to have the thyroid hormone to be secreted, and then now you can have de-iodination later. So thyroid hormone secretion is going to be later. Iodine trapping, okay, you want first to trap iodine, and then after the trapping of iodine, remember what you want to form is iodine phase. So you are first going to in the blood you have got this iodine and iodide. Okay, you are going to have iodine, you trap it from the blood, and then you do form your iod. You I don't know which one you are forming. It should be iodine or iodide, one of those. Okay, so when you get to trap your iodine, and then you are going to have oxidation iodide. You oxidize your iodine so that it becomes the iodide. Now let me just check to see which one is charged and which one is not charged, because they are confusing. Okay, okay, so the first thing that will happen is that, let me start how it starts from the head so that it will be easy in case they change any step. You are going to have thyroid releasing hormone, which will be released from the hypothalamus. Thyroid releasing hormone. Thyroid releasing hormone will go to the anterior pituitary gland to release thyroid stimulating hormone. Thyroid stimulating hormone will stimulate the follicular cells to make thyroglobulin. So we're going to have thyroglobulin formation. Okay. So where is thyroglobulin formation? So that is what we are going to put as 1. And then after that, you are going to have now your iodide being trapped from the blood after you have formed your thyroglobulin. So you are going to have iodide trapping. So thyroglobulin is something like this. You have formed a molecule which is like that. Okay, something like that. And then when you trap your iodide, now you're going to oxidize your iodide using what is known as thyroid peroxidase. So that will be now oxidation will be the next step. And then after you do the oxidation, now you're going to have the iodination of tyrosine. So now the oxidized iodide is going to be added to tyrosine. So that is going to be what? Iodination of the tyrosine. After the iodination of the tyrosine, you are now going to have now, because imagine this is tyrosine here, and then you have added iodine to it. So you are adding iodine, iodine, there iodine. Some of these iodines, they have got, actually some of these iodines have got one tyrosine, others have got two tyrosines. Now let's not say this is tyrosine. Let's say I've got iodine attached to one tyrosine, that is called diiodotyrosine. You are also going to have some iodines which are attached to two tyrosines, like you are also going to have monoiodotyrosines, diiodotyrosine. So after your iodination, you have added iodine to tyrosine. Now these can be now coupled. Some of those which have got the diiodotyrosines can be coupled with monoiodotyrosines. Di and mono are going to form tri. So that forms now T3. And then the di and the di, that will form T4, which is thyroxine. Okay, so coupling is the next step. Where is coupling here? Did they even give it? Okay, there is no coupling. And then after that, you are now going to have endocytosis of the thyroglobulin. The thyroglobulin that we had formed the area now is going to come in. It's going to be endocytosed, right? So do we have any endocytosis here? It's not there. Okay. And then after that, we are now going to have the enzymes working on T3 and T4. And then we are going to have exocytosis, though that is being released. Okay, so the condensation is actually the same coupling here, so that will be the next step, step 5, which is condensation. After then, the thyroid hormone can be, when it has been formed now, can be stored. Okay, when it is stored, when it is needed now to be used, it can be secreted. Okay, so those steps, is that okay? Okay, so